We'll do it live. All right. Nope. Okay. So first hour 5-6, part one. This is the first part of 5-6. So this is asking us to represent the inverse of a relation using tables, graphs, and equations. Now, inverse functions, and the word inverse is used loosely in mathematics, I think a little too much. So whenever we're dealing with inverse relations and inverse functions, I always think about this word here. So I'm going to make this as big and bold as possible. Aiden Steffensmeyer, I know you can read, young man. What does that word mean? Or what does that word say?
Switch.
That's exactly right. That's exactly right. So when I hear the word inverse function, I'm thinking about switch. So what is going to switch? Well, what do we know about functions? Functions have some sort of biscuits. They have some sort of an input that produces an output. They have a domain and a range. Inputs and domains, what is that describing? What variable is that describing?
X.
X, yeah, so these are all of your X values. Outputs and ranges are describing the what?
Y.
The Y values. So, when it comes to inverse functions, what is going to switch? Our inputs, our X values, our domain is going to switch with the outputs, our Y values and range. These are going to switch places. Alright? So we're going to do this really neat little switcherooski. Okay. So let's do this down here. What I want to do is I want to look at this function in two different ways. So let's start by creating a table of values. If I create a table of values x, y, and here we have y equals x squared, I'm going to go -2, -1, 0, 1, and 2. When I plug a -2 into that function, what's the y value going to be? What's f of -2 for this function? F of -2. The function is f of x equals x squared. That's our function. Plug a -2 in there. What's the output?
2x squared? Maybe?
Oh, is there an x in here?
No.
What's -2 times -2?
Positive 4?
That's it. When I plug a -1 in, what's my output? A -1 times -1.
Just
Multiply. What's 1 times 1?
Oh.
1. Yeah, 0 times 0. Yeah, don't worry. I know it's early. 1 squared is 1 and 2 squared is 4, right? I hate being sick. Alright, so if an inverse function or an inverse relation, what do I need to do with my x and y values? Alright, so this is where y equals f of x. So what would my inverse be? Inverse is going to take all of those x values and they become y values, right? When I say switch, my x and y values are going to switch. Okay, so my x and y values switcherooski. So here, my x values are 4, 1, 0, 1, and 4. My y values are -2, -1, 0, 1, 2.
Is that all? Do we have to show transfer it, or we just switch?
We just switch it. There's no math to do here when I'm dealing with a table of values. Right? When I'm dealing with a table of values, all I do is I take all of my x values and I make them y values. I take all my y values and I make them x values. I'm just going to switch them around. Now, the question that we really want to ask ourselves is the inverse also a function? Is the inverse also a function? Ooh, well, that requires us to define a function perfectly to be safe here. So down here, what is the definition of a function? A function has one output for each unique input. All right. So, -2 for x. All right, are you done writing that down? Oh, you're texting. Sweet. Great. Glad to hear I've caught your attention today. All right, so a function has one output for each input. All right, so -2. So looking at the original function, -2, what is the output for -2? 4. Are there any other -2's on my input here? No. All right, so my input is all unique values, and they all point to just one other value. All right, so let's go to the inverse. Here I have an input of 4, correct? What is the output for that 4? -2. What is the output for this 4? Yeah. If I put one pizza into a pizza oven, can I get 2 unique pizzas coming out? No. That's why I think about functions as pizza ovens. If I put one pizza in, I get one pizza coming out. Right? You see that in the back of Casey's every single time, right? You could see that one uncooked pizza is only going to produce one cooked pizza. Right? That is a function. That is a mathematical function. Because one input has one output. Here, the inverse had an input of 4 that produced an output of -2. And then another time, whenever I put a 4 in, I got a +2 that came out. So, in this instance, the inverse is not a function. Because one input of 4 produced 2 unique outputs. Same story goes for 1, right? 1 produced a -1 and 1 produced a 1, right? So that means that our inverse is not a function. All right. Now, it also says, how can we represent this algebraically? How can we represent this algebraically? So without a table of values, if I just start with the function, how can I find an inverse? All right, so if I start with the function f of x equals x squared, the first thing I want to do, and I'm going to write my steps out over here, I want to replace f of x with y. I know, this is just housekeeping. Really, this is just housekeeping. I'm not doing any mathematics. I'm just changing the way I view this. Because f of x and y are the same thing, I can replace this with y equals x squared. Hey, Talia, what's that giant word that we wrote on the top of this page? Yeah, so the second step here, we are going to switch x and y. So where I see x's, I'm going to replace them with y's, and where I see y's, I'm going to replace them with x's. So what does that look like here? Well, we're going to say that x equals y squared. Ooh-wee. The third thing we want to do is solve for y. Now, what do I need to do to get y by itself over here? Square root. So if I square root this side and I square root that side, I get y equals, when I'm solving and I take a square root, I end up with the positive and negative version of that. I'm going to rewrite this in terms of y equals. Since y is on the right side, it kind of makes me feel a little left-handed, and I don't like that. So y equals the square root, plus or minus the square root of x. And that is our inverse, right here. How many inverses did we find? We found two. We found where y equals the positive square root of x, and that y equals a negative square root of x. So, if I were to look at that on a graph, where did my calculator go? There she is. If I wanted to see what that looks like, we were looking at big numbers. I would go here, nope, here, home. We're going to graph this. I'm going to clear that out. I want to say that y equals the square root of x. Nope, that's not what I wanted. Yeah, that's what I wanted. Okay, and then I also want y equals negative square root of x. Okay, and when I go graph these, what does that look like?
A parabola.
That looks like a parabola. Right, and if I, most literally, I turn my calculator so that you can see it normally, right? That's just a normal parabola. However, this parabola, there's my y-axis, there's my x-axis. My parabola is sideways all of a sudden. My parabola is sideways. And this, we can take a look. You know that x is the input, right? When my input was 4, we got a positive 2 and a negative 2. When my input was 4, we got a positive and negative 2, right?
I feel like I could tell. I could tell that it was a parabola because it was like it was negative 2, 1, and then 1, 2, which literally on a graph will always do that.
Right. Yeah. You have those pairs, right? Those pairs where it goes down, 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 up, 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 up. That sort of down, 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 up, 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 up. That sort of symmetry, right? Will always create a parabola. Yeah. So here, one way to easily figure out whether or not a graph is a function, if I draw a vertical line and it crosses that graph twice, meaning that 4 had a 2 and a negative 2, right? So if I draw a vertical line on a graph and it crosses twice, then it's not a function. It's not a function at all. Alright, so that's how we find it algebraically. We're going to replace f of x with y, switch your x and y, and then go solve for y. In this instance, we found that the inverse was not a function. Alright, let's keep cruising. We already looked at those graphs, right? So we're going to skip that because we already saw those graphs. Let's try this again down here below. So what is step 1? When we're going to solve this and go find it algebraically.
Make it equal to 0.
Not equal to 0. Yeah, well, before we solve for y, I got to switch it from f of x to y. Yeah, so y equals 2x plus 1. And what's step number 2? What does it say, Aiden? What's the the giant word here? This is the crux. I have to switch my x and my y values.
So it'd be just 2y
plus 1.
Okay.
Yeah. And now we got to go solve that for y. Okay?
Equal to 0.
No. Solve it for y. X equals 2y plus 1. The only time we really want to set we set equal to 0 is whenever we're trying to find numerical values. Right now we're not finding a numerical value. We're finding a function. Functions have an x and a y. Always. So in this instance, I have an x and a y. Right? I just got to go solve for y. So if I want to solve this for y, what would I do first? Yep, subtract your 1. So we get x minus 1 equals 2y. What's your second step if you're solving this for y? Divide by 2. So I'm going to divide every single term by 2. I don't want this one big half over here, like everything divided by 2, because I need to see what's happening. I now have y by itself, so I like to write y on the left-hand side. And now I'm going to simplify this to see what's happening. This is really 1/2 x minus 1/2. And now this is our inverse. So that inverse function will be able to graph. If I go negative 1/2 on the x-axis, boop, and it wants me to go up 1 over 1, so it'd be a half here, and a half here, and a half here. I know we're dealing with halves on a graph, and it's nasty, and I'm so sorry. But this guy, big guy, SpongeBob, Pantle, Kai. There we go. No, that's a lie. Why is that a lie? What was my slope, Talia? Yeah, my slope was 1/2, not 1. Man, I can't believe you let me go that far. Biscuits. Oh, we gotta try it again. I'll do it again. We start at negative 1/2, we go up 1, and to the right, 2. 1/2. Rise over run. Up 1, right 2. Up 1, right 2. There you are. I see you now. Okay, that's a lot gooder. Okie dokie. Now, can that graph be considered a function? Yes. So here's what I want you to take away from this. Is a graph a function? Question mark. Something called the VLT. That is called the vertical line test. Alright, so if any vertical line crosses a graph twice, it's not a function. So is there a vertical line that I can draw on this graph that will cross that line twice? No. So is this a function?
No.
Absolutely.
Oh.
Yes. So let's write out the rules here. If any vertical line crosses twice, the graph is not a function. Otherwise, it is a function. So that's how we can determine if a graph is a function. I want to see now, though, let's ignore all this. Let's just focus in on the graph for a second. If I graph the original, y equals 2x plus 1, what can we tell about this graph? So 2x plus 1, here's my 1, here. We're going up 2 to the right 1, up 2 to the right 1. Alright, so this graph right here. This is the original. So we have the OG and the inverse. Alright, so the original function and its inverse. What do you notice about these two graphs? All right, so they cross at -1, -1. True.
I don't know. Like, I don't know the word, but like, I guess in my mind, they look kind of like symmetrical.
Yes.
Like,
Yes. How would you say that they're symmetrical? Right? So take a look at the flags that I have in the back of my room.
Maybe like,
Seriously,
I guess mirrored.
Yeah,
Kind of
yes,
weird.
yes, yes. That's exactly right. Look at the Jamaican flag back there. The black, gold, and green one. How is that symmetrical? What could you do to that graph, or to that flag, so that it would land on top of itself?
You just mirror.
You would mirror it, or fold it in half.
Yeah.
Could you fold it long ways?
I think so.
Yeah. Could you fold it hamburger style as well?
Yeah.
Yeah. Now, here, this graph, it is mirrored. Like, you're absolutely right. You could mirror this thing, and I hope this works. I wonder if I can do it on video. Come on, girl, give me a mirror. Oh, that's really disheartening. I used to have some really cool beer. Oh, biscuits. Oh, well. Yeah, no, so you're absolutely right. There are two ways that we can mirror this thing. I could mirror it this way, right? I could fold this thing here, and this half of the graph would land exactly on this half of the graph. Or I could do it this way, right? Right? Okay. So let's take a look at the last one that we did. We had this guy, big guy. What if we did y equals x squared? All right, so this is going to take a look at, I don't need all syntax error. What are you doing? I just want to plot that thing. Really, don't need this. Let's navigate. Let's navigate over this way, down this way, and zoom in. Man, that's this is boots. Yo, dude, that's not what I want. Why is it not giving me what I want? Oh well. Pan and zoom in or out. Pan that way, but can I just change the x-axis to be? Oh, well. You know what? We'll see it another time. So this can have two lines of symmetry. All right, fine. Let's keep cruising. Let's roll it over. No. You know what? We're going to do it up here. We got time. Right? We got time. We got 7 minutes. All right, so here's what we're going to do. We're going to look at y equals x squared and y equals plus or minus root x. All right, so we're going to graph both of these functions. Y equals x squared goes 0, 0, 1, 1, 2, 4, 3, 9, which is Spanish for 9. 1, 2, 3, 1, 2, 3. All right, we want to try and be as accurate as we can with this graph because we got some details that we want to sneak away from this. All right, so we have that graph. And we have y equals the positive square root of x, and we know that guy goes 0, 0, 1, 1, 1, 2, 3, 4, 2, 5, 6, 7, 8, 9, 1, 2, 3. Wait, did I make that wrong? I sure did. This graph is bigger than I thought. There's going to be somebody on the internet that's going to correct me. There you are, here and here. Okay, so we have this graph here, 0, 0, 1, negative 1, 4, negative 2, 5, 6, 7, 8, 9, negative 3. Okay. All right. Are we okay? Do you see both function or both graphs? Because we already determined that this one, right, sideways parabola, not a function. But what can we determine is the same about this graph and this graph? So this pair here has the same symmetry as this pair here. Okay? And as you said, that symmetry is a mirror. How would I draw the mirror here that would be the same mirror on the other graph so that these graphs land on top of each other? What would that mirror be?
I mean, I guess you like, I don't know how to describe it, you do it like that.
Yes, that's exactly right. Yeah. So that mirror would go this way, right?
Yeah.
So challenge. What is the equation of the line of symmetry?
Oh, I don't know. Would it not, wouldn't it just be like,
I want it in y equals mx plus b form. If I had cash in my wallet, I would give you cash if you got this. I might just have to give you Seymour. I'll give you cash Seymour if you get this right. So you're going to purposely get it wrong? That makes sense. I would too.
I give you my best guess.
All right. If I have a $1 bill in my wallet, I will give it to you if you get this right. Talia, what's the equation for that line? Oh, you got this. My best suggestion, instead of looking at this one, instead of looking at the parabolas, go down to these two lines. Go down to these two.
I put y equals 1x plus 0.
Say that one more time, Aiden Steffenmeyer.
Y equals 1x plus 0.
Y equals 1x plus 0. Talia, clean that up. Y, not 1, but y equals x. That's it. That's the one. Do I have it?
I know I couldn't put
Do I
y
have it?
equals 1,
Hang on.
because that would just go up.
Listen to the sound of money. Yeah, that's right. I'm a 43-year-old child. Oh, Bubba. I'm so sorry. All I have is
I just gained money and knowledge.
I have a Snub Bull Pokemon card. That's it. Oh, and
Is that, do you put that in your
And
ID slot?
no, not in the ID slot. It gives me 2 slots for cash. So the back side is where I keep my Snub Bull. And then
You'll get into a battle.
yeah, well, you got that right. Do I have any? Oh, I do. There's something really cool in here. Hold on. There she is. Look at that.
That is cool.
Isn't that awesome? Yeah, it's called a challenge coin, and I got it from the Kansas Honor Flight. I was never able to make it to the Army or the services because I'm too much of a wuss. So I had to wait until Honor Flight offered them. So I purchased it. It's not stolen valor, I promise. Okay, let's focus. The equation for the line of symmetry is y equals x. So if I draw that line, y equals x, 1x plus 0. God, I'm so proud of you, Aiden Steffensmeyer. It's so good, dude. That's this line right here. All right, that is, and I'm going to make it dashed. All right, that's our line of symmetry for every function and its inverse. Okay, so I'm going to write that out. For every function and its inverse, the line of symmetry is y equals x. You know why it's that way? What is step 2 of the algebraic process to finding an equation, an inverse? What is switch your y and x? at the moment that I said, instead of y equals 2x plus 1, and I switched my x and my y values, I most literally took this xy pair, which used to be 1, 3, and it then became 3, 1. The 0.25 became the 0.52. Right? So that coordinate point 1, 3 became the coordinate point 3, 1. I switched my x and my y values. And when I switch my x and my y values, I am very much reflecting over that line, y equals x. And it should make sense that these lines cross at -1, -1, where y is the same as x. Right? So, those are the ideas that we're going to be contemplating through this 5-6 unit.
Line symmetry still be y equals x on that one?
Always, yeah, absolutely. If I started at 0, 0, and up 1, like that, right? That line, that's your line of symmetry, right there. Right?
Yeah.
Really good. Really, 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 really good. All right, questions. Talia, questions about it? Yeah, good. Aiden, questions? All right, so the issue, right? The issue that we have with this quadratic, the issue that we come across is that the inverse is not a function, right? The inverse had two outputs for one input. So, when I roll it over here, that function y equals x squared, under what domain will the inverse also be a function? Now, we can quickly determine with horizontal lines from the original function. So if we look at the original function and we have a horizontal line that crosses twice, then the inverse is not a function. So, if the inverse has two x values for the same y value, the inverse will not be a function. We can restrict the domain in many different ways to create a function that will have the inverse be a function.
Should we not just be able to do like negative infinity to positive infinity for domain?
Well, yeah, so what happens when I go negative infinity to positive infinity with the domain is that these values would still produce, these would still have the same y values. So how can I cut this parabola so that I don't have any repeating y values?
I guess you could use the line of symmetry.
Yeah, the axis of symmetry is exactly right. If I were to cut this thing here at half at the axis of symmetry,
And then when you write it down, you'd have a union.
well, no, there's still just one set of values. What if I, instead of negative infinity to infinity for this, how can I restrict the domain? It would start at what?
0.
0 and go to?
Positive.
Yeah. So the new, I'm going to say it like this instead of new. I'm going to say the restricted domain. The restricted domain would be
We call it the RD.
0 to infinity. And I am the restricted domain. That's the new. Yeah, thank you, Aiden. I appreciate you coming up with symbols for us to make things easier. And now notice what they did here. Right? So notice that they cut off that left-hand side just as you said, right? So there's no more repeated y values. And then they only graphed, on this third one here, they only graphed from 0 to infinity. Or, look what they said in this little box, restrict the domain of f to be x greater than or equal to 0, or 0 to infinity, like you said. Those are the same. All right, good job. Really, really good job. Really, really good job. All right, so then on the bottom down here, what they did is they took that restricted domain for y equals x squared from 0 to infinity. They restricted the domain so that the inverse, ooh, they got new notation. Woo! The inverse function is just y equals square root x, the positive side, right? And right here in this box it says the graph of the inverse function of f is the reflection of the graph of f of x across the line y equals x, just like you said. But I'm more excited about this right here. F inverse of x. Ooh-wee. So let's make a little note over here. Note. The OG function, the original function. So the original function. the original function we say f of x, right? The inverse is written f inverse of x. It has a little exponent -1. Alright, so f negative 1 of x. That says f inverse of x. F inverse of x. Okay, let's see if we can do one more. We only have 1 minute left. Oh yeah. Well, I think that's a good spot to stop, actually. That is a good spot to stop. That's a good